All right, so looking at exponential decay, you can see that the form there. It's really very very similar to the exponential growth, except for the minus sign. Right, all the p of t or the y, the a, the r, and the t, all those things mean exactly the same thing as they did yesterday. Just I think the big thing that's going to be coming out of as we move forward. On the worksheet, it's all like everything's delineated. Like, here's the growth problems, here's the compound interest problems, here's the decay problems, right? When we get to the quiz next week, that we're going to give you as the formulas, and we're going to give you 3 problems, but it's not going to say which one to do when. You really need to be able to look at the problem and say, okay, here's something I noticed about this problem, and that means I need to use this formula. Here's something I noticed about this other problem, so that means I'm going to use this other formula. So what is it within the situation that says you need to use the growth formula? Really it's going to be something along the lines of, it's going to say, the population has grown exponentially. Right? There's a growth problem. We look at this first problem here is talking about the value of a snowmobile decreasing. That's a decay problem. And things are decreasing, going down. When you look at these investment problems, what is it that's different about them? What's kind of a keyword here that will let you know which formula to use? And probably for me that word compounded. So when you see that word compounded, that talks, it has to deal with that end value. So just that problem solving skill, guys, like what's the key information there? How does that then lead you to do this, this, or this? Okay, so again, it may seem really easy right now because everything's chunked, but in the future it needs to be, you got to pay attention to those little details. So one of the main applications of exponential decay is depreciation. Sorry, my iPad's being rude. And depreciation is just, it's probably a concept you guys are familiar with, even if it's not a word that you know. But it's just the decrease in the value of an object, usually over time, usually due to like wear and tear. So like if you buy a TV now, in 5 years it won't be worth as much. You buy a car and it starts to lose value. There are certain things that you can buy that can hold value or gain value, but most things that you buy lose value over time. So that's what depreciation is the decrease in value of an object over time, usually due to wear and tear. So that first example we're doing, I guess I'll relabel these for you guys. So Y, would be the amount, or it could be a population still. You could look at a decrease, declining population. So amount or population at a given time. A is still that initial amount or population. And R is still the the rate of change, and it's still, again, that idea that it needs to be written as a decimal, and that again is usually the most common mistake, is not getting that into the appropriate decimal. Rate of change as a decimal, and then T, of course, is time, and again, this is usually in years. For everything that we do, it'll be in years. But again, if you're looking at a colony of bacteria that was dying, you would want to look at that over hours or days, not years. But we'll be focusing on bigger things. We'll have use years. So first problem here, snowmobile, its value is decreasing at 10% each year. Started off at $4,200. write a model equation, right? Write the exponential decay equation, and then we'll go and do the specific times, just like we did yesterday. So what am I expecting to see there when I say write a model equation? Everything should, only A and R should be values. Everything else should be the set, and especially that T is really what I'm getting after, is that the T should stay a variable. So I see my A value, I see my R value there. So I would say that Y equals 4,200 times 1 minus 10% would be 0.10, or just 0.1, depending on how you want to write that. I prefer 0.1 to the T. Okay, so I'm wanting to see that T there still. Amazing. Okay. This would be your model equation or your general equation. If I ask you guys to write that, that's what I'm looking for. Then we go ahead and look at each of these. I didn't see it when I glanced. Maybe you did, but maybe I missed something. If you want to do that math right here, you certainly could. 1 minus 0.1 would be 0.9. So you could put 0.9 to the third power, if you want to, or you can just write it as 1 minus 0.1. We're going to take that to the third power for 3 years, right? So what's the value of this snowmobile after 3 years of decline? Really should be pretty straightforward as far as typing. 4,200, 1 minus 0.1 to the 3, right? This is money, so appropriate rounding for money is 2 decimal places. So, we notice this problem doesn't have 2 decimal places, but just think about that represents $3,061.80. So you would need to put that extra 0 on the end of it to make sense of that number. Hardy har har. $, 3,061.80 would be our value after 3 years. Five years, we'll do 10 years. So 4,200, 1 minus 0.1, all to the 5th power. $4,200, 1 minus 0.1, all to the 10th power. Remember, if you have a TI calculator, if you hit second enter, it'll bring up the last thing you typed, and then you can just edit it really quickly. You don't have to retype the whole thing. Or if you're using this app, all I have to do is tap the thing up there in the top left. It brings it down for me. I delete the 5, or delete the 3, hit the 5. There's my answer. Do it again. Delete the 5, get the 10 in there. There's my third answer. So $2,480 and then 6 cents with appropriate rounding. $2,480.06. And $1,464.45 with appropriate rounding. $1,464.45. All right. Yeah. Cool. Thanks, Jeremy. Have a great YouTube. Anything about decay seem weird? Yep. Exponential growth, but with minus sign. Easy peasy. You good, Caleb? So depreciation is one big aspect of exponential decay. Another big one is carbon dating. Okay? The idea that we can use the predictable radioactive decay of elements around us to figure out how old things are. So something that happens every time you take a breath in is that you inhale some an isotope of carbon called carbon-14. So it's a radioactive isotope, but it's not radioactive in a way that you would turn green and get angry. So it's radioactive in it, and that it decays at a predictable rate. So every time you take a breath in, breathe some in. So the idea is that you have 100% of the carbon-14 that you could have in you right now. Okay? As soon as you stop breathing, aka die, that carbon-14 starts to decay. The idea is that if you took all of the carbon-14 that was inside of you and you balled it all up, you've got this little ball of, weighs 1 pound carbon-14 sitting there, and then in 5,730 years, future Aiden will come by, he'll measure that ball of carbon-14 and found out that half of it has gone. It went from 1 pound to half a pound. And then 5,730 years later, future Mason comes by and says, he weighs it, and now it's down to a quarter pound because half of the half is gone. And then 5,730 years later, future Caleb comes by and he measures it, and he's like, oh, now it's down to 1/8 of a pound because half of the quarter that was there is now gone. So every 5,730 years, half of it goes away. It's not that you lose one half and then the next time the other half goes away. Right? Half of what's there goes away. So it's always decreasing, right? But it would never go to zero, right? Because it's just going to get smaller and smaller and smaller and smaller. And it would never go to zero. Just like when we saw those graphs and how they hit that asymptote, they don't actually ever reach it. They're just going to get really, really close to it. Okay? So that's what it means to have a half-life. You lose half of what's there. Okay? So yeah. Okay. So that's what that 5730 is about. That's why there's this number here. If we give you guys a problem with carbon dating stuff in it, the equation will be given to you. We're not going to ask you to develop the equation. Okay. The P here stands for the percent remaining. That's what we hear. The 100 is that 100% the whatever started with. Right. You always start with 100% and it declines from there. Okay, so that's the initial amount. The starting amount is the 100%. 0.5, it's there because it's the half-life. Every 5,730 years, half of it goes away. And of course, there's T. So you can see how structurally this is very similar to the decay equation, except for this division up here is the only thing that's different. Okay. Yeah. So and carbon-14 is used when things are not really, really old, I'm talking in the tens of thousands of years old. You need something that's trying to date something that's millions of years old. They use other elements that have longer half-lives. There are other elements that have much longer half-lives. I think there's a cesium isotope that they use for some really old stuff. Okay? But we just give it this general name of carbon dating. But we don't always use just carbon to do that. So the real goal of this problem, though, is to be able to do this down here. Okay, that's our end goal, is going to be able to figure out how old this bison bone we found was. Okay, but to do that, we're going to need to collect some data. We're going to need to make a graph, and then we're going to be able to use our graph to then answer this question. Okay. So in order to make a graph, we need some points. So that's what we're going to do here first. Right? And I have given you guys some values here. Also, just that thought of at time 0, where do we start? Really, our kind of our starting point. Okay. So I'm going to plug in 0 for time. So 100 times 1 minus 0.5 to the 0 divided by 5730. You can actually do this one in our heads. 0 divided by 5730 is 0. Anything to the 0 power is 1. And 100 times 1 is 100. So plugging in 0 gives us 100, which should make sense considering what I said. At time 0, that's immediately upon the animal or the plant's death. As soon as that thing stops interacting with the air, that's time 0. So you should have 100% of your carbon-14 at that moment. Then everything after that's when it starts to decrease. Okay? So time 0 is the start of the problem. So start of the problem would be the end of the animal or plant, whatever we're talking about. What about 2,500 years later? What about 5,000 years later? What about 10,000 years later, right? What percentage of carbon would be left? So plugging that in. So 2,500 divided by 5730. So kind of like we talked about yesterday, because that exponent is complex, it's not just one number, we need to make sure that our calculator understands that. And so you're going to make sure you put parentheses around that when you go to type that in. Okay? So that's it. That's something you need to take control of when you're typing. It's making sure your calculator understands what you're asking it to do. So I'm going to go ahead and type that in. 100, 1 minus 0.5, caret, 2,500 divided by 5730. And double check your numbers. Really easy to mistype something and have that screw everything up. And the number one most common mistake is the exponents, the rate stuff, not turning those into decimals correctly. Definitely really high on the mistake level is just mistyping. Okay? There's nothing you can do about that besides just slowing down, checking your answer, checking your work. I'm going to go ahead and round this to just the nearest percent. We're going to be graphing this. There's no way we're going to tell the difference between 73.9 and 74. So I'm just going to round this to the nearest whole percent, so 74%. Okay, I'm just going to do the rest of this. So 1 minus 0.5, 5,000, that's 500. 5,000 divided by 5730. 100 times 1 minus 0.5, 10,000. Watch that 10,000. Add too many zeros, not enough zeros. Really easy mistake to make. So what's 5,000 get us to the nearest whole number? Yep. Did you type 0.5?
0.
4%? Is that to the nearest whole number? Yep. Okay. What about 10,000? 30? Okay. That's good. That's it. So we've got our numbers, right, which means we need to go think about our graph now. So we're going to plot points, so we need axes, right? What would be a bad idea here would be to put those axes there in the middle. We're talking about the age of things, and so 10,000 or years, we're not going to have negative time. Okay? We're not going to have negative percents of things. So if we put our axes in the middle, all of this space would get wasted. And then our picture would be up here in this corner, smaller than it needs to be. But you guys should know from science, your axes should go on the left side and and on the bottom. So we look at the positive realm of things. So I'm going to put my axes on the bottom and on the left. Something else you definitely talked about in science, and we talked about it some in fall semester. We haven't talked about it for a while. It's just that idea between the difference between the x variable and the y variable as far as what they represent. That the x-axis always represents the independent variable, and the y-axis should always represent the dependent variable. Okay? And the dependent variable changes because the change happens in the x value. So the y's should change because x is changing. So you need to decide which of these is independent, which of these is dependent. You should be asking yourself, does the time change because the carbon is changing? Or does the carbon change because the time is changing? And one of those should make sense, and one of them shouldn't make sense. Okay? So I think, June, does the time change because the amount of carbon is changing, or is the carbon change because the time is changing? Carbon changes because time changes, right? So that means the carbon depends on the time. So that means that's the dependent variable, which means it's the y variable. Okay. So I'm going to put percent remaining on the y-axis. Make sure you give yourself some space because you're going to have to write some numbers there. All right, so our y-axis is our percent remaining. And you guys will be expected to label things. You guys have a problem just like this on your, that's a little percent on there. You guys have a problem just like this on your homework. Whoa. Then I get grouped. So that means the x-axis is our time. And that's just in years. So there's really only one correct way to do that. X should be time, y should be the percent remaining. Flipping them back and forth is not okay on this. The other thing we need here is numbers. Right? So what scale do we set up? What should I be counting to? This, of course, that left side should be 0, the bottom should be 0. But what number do we need to get to over here on the right side? What number do we need to get over here on the top? There's a little bit more of an art to this sometimes versus like a hard do it this way. Okay? But it is hard that the x-axis should be the time and the y-axis should be the percent. That's the only correct way to do that. Something that is kind of set when you do scale things, like when you choose to, what you're going to count by, that scale has to be consistent. I look at each of those tick marks and I say, okay, that first tick mark's going to be 10 years. And the second tick mark's going to be 100 years. The next one's going to be 1,000 years. That is not okay. The spaces have to represent the same amount of change. I can't go from 10 to 90 to 900. That's not okay. So whatever you pick, it has to be consistent. Can't change. So how do you decide what to pick? Right? Well, how far do we need to go? We look at our, the numbers that we need. It's not grouping. As far as the time goes, our biggest time is 10,000. We need to go from 0 to 10,000. So I probably want my, my far right to be 10,000. What I could do, I could have that 10,000 be here and go beyond it. That's okay sometimes. But what I'd like to see you guys do is basically use as much of this space as possible for your graph, that you're not squishing it down into a corner here, kind of the same way we didn't want to squish it up into the corner over here. If we have all this space, we should use it because that's going to help us get a better answer, a better picture, and then a better idea of what's happening over here. So the bigger we can make our picture, the more accurate it could be, and help us figure out this answer better. Okay? So I don't want to push all those numbers to that left side. I want to stretch them out as far as I can. So if I need to get all the way to 10,000, well, there's 20 boxes there. I'll just tell you that because I know that. Okay? When I get to 10,000, I have 20 spaces to do that. If I count every other box as 1,000, we'll get there. Okay? So I'm being consistent because each 2 spaces is 1,000 years. I can use 2 spaces, they just have to stay, each 2 spaces is still 1,000 years. That's consistency. Okay? I've given you some information there. You should be able to look at that and know what I'm counting by. That's 0 and that's 10,000. You count how many spaces there are in between. You should be able to figure out that each one of those is 1,000. Could I give you more information to make that a little bit easier? Sure. I could label that 5,000. I could even label one of them as 1,000. I'm not a big fan personally of going through and labeling every single one, because then I have to write it really tiny and it gets pretty messy pretty quick. I'm not a big fan of that. Okay. So I'm more here, less is more here. If I do that, you really should have pretty much everything you need to know. Okay, that first chunk's 1,000. Okay, yeah, it looks like the next chunks are all 1,000 each. It makes sense. Okay. Again, a lot of that's just kind of my personal opinion here. There's no set way to scale things. So this is just me having done this over and over again for years. This is kind of the feeling I get about it. There's enough information there that you guys should be able to understand what I'm saying. It's kind of the same thing I'd expect from you guys. Are you giving whoever's looking at your graph enough information to make sense of it? Okay. So the other side of that is the percentage side. How do we scale our y-axis? Where do we need to get? Well, 0% is the least amount I can get. It's the most I can get, 100%. So how could I count from 0 to 100 in 20 spaces? Well, we could count by 5s. But I don't want to make little tick marks every box. So again, what I'm going to do here is just count every other box as 10. Okay? Again, this is not the only way to do this. It's just the way that works easily. Every other box is 10. Now these numbers are smaller, so I'm a little bit more inclined to go ahead and write those. But again, the idea is that you need to give somebody else enough information that they could come along and read your graph and go, oh, okay, I actually understand what's going on here. If you don't label your axes with words, if you don't label your axes with numbers, all you have is dots and a line drawn on a piece of paper. And how is anybody supposed to understand what that means? So the labels have to be there, the scale has to be there if you expect somebody to understand what you're doing. Okay? So there's the expectation. Your graph should look like this. As far as having labels and scale on it. So let's find those 4 points, 0, 100, right? 0, 100 is up there in the top left corner. 2,500, 74. So there's 2,000, there's 3,000, so 2,500 must be there. 74, well, that's really close to 75 as far as I can tell. Maybe just a hair below 75. There's 75 because that's between 78 and 80. Right, so just a hair below that. 5,055, that should be pretty easy to find. 10,030, that should be pretty easy to find. So you get your 4 points plotted. Remember, drawing here is a curve, right? It's an exponential curve. So do your best to draw that as a curve. Do not draw it as a straight line. Your graph should look slightly different than mine because we're all doing this by hand. But it should look pretty much like that. Somebody in third hour asked a good question about if there should be an arrow on the ends. Mathematically, there should be an arrow on both ends. Realistically, there's no arrow that goes that way because we can't go into 0 time and above 100%. So realistically, there would be no arrow there. We could have an arrow on this end, even though it doesn't really do us any good because we can't see what's happening over there. But yeah, if I were going to do that, I'd probably only put one on the right end, just because we could keep going down and forward through time. So this last little bit, we're going to use that graph to estimate. Okay, you're going to get an estimate, and your estimate should probably end up being a little bit different than mine because your graph's going to be a little bit different than mine because you drew it by hand and I drew mine by hand. Okay. We have a bison bone that we found. We've done some tests. We found out that it has 37% of its original carbon in it. So we want to figure out how old it is. So 37%, where is that? Somewhere up in here. There's 35, there's 40, so somewhere kind of in between those two. So you want to draw a straight line. So it's not a straight line. Okay? So you might want to get like a little idea out, find your ruler out, use the side of a book, right, to draw a nice straight line from where you think 37 is all the way over to your graph. Wherever that hits, you then draw straight down. And then you interpret that answer. So I'm getting something like, there's 5, 6, 7. I'm getting something that's like almost right on 8,000 for me. This is the third time I've done this today. This is the third different answer I've gotten because my drawings have all been slightly different. Okay, so that's getting really close to 8,000. I can't really tell the difference for me. So I would say it's about, using an estimating word, about 8,000 years old. Okay, you guys should have something in like the 7,500 to 8,500 range on your answer. About, around, approximately. I would just round to the nearest hundredth, just to best of your ability. What's it look like? Does it make sense how we use the graph there to go from the percent to the time? Okay. You guys good out there, Tion? Does that make sense? Kyle, does it make sense? Jubal, does that make sense? Right. And you guys have a problem just like that on your homework? Yeah. That's the same.